Thanks again for joining our webinar, What's New About Off-Grid Solar in Hazardous Locations. This is a joint webinar between Morningstar and SunWise Power and Battery. We'll be recording this broadcast and emailing you a link to the recording before the end of day tomorrow. And we've also attached a PDF copy of the slide deck that we're using today, and that's in the handout section of your GoToWebinar page, so you can go ahead and download that right now. As you listen to the webinar, feel free to type any questions that you have in the questions chat on your GoToWebinar console. We'll address your questions at the end of the webinar. And with that, let's go ahead and take a look at the agenda for today. So I'm going to start off introducing you to today's presenters, Brad and Errol from Morningstar and SunWise. And they'll define what a Class 1 Division 2 Group A through D hazardous location is. They'll also discuss the loads that are best run by solar power and the new capabilities in the HAZLOC zone because of the larger feature-rich charge controllers that have recently achieved HAZLOC certifications. Brad and Errol will cover system components and system sizing examples, and also trends related to system upgrades. They'll provide a summary and then answer your questions in the Q&A session. So let's go ahead and next slide, we'll take a look at the presenters that you see here. Errol Rankin, VP of Sales and Technology with SunWise, and Brad Burwald, Senior Product Manager with Morningstar. Brad, you're up first, so please go ahead with the presentation.
Okay, thanks very much. Welcome everyone. It's great to talk with you today, and I appreciate partnering up with Errol on this. Both of us have worked in this industry for significant amount of time, and I've definitely supported oil and gas applications throughout the years as my time in product management as well as in sales. And if I believe I even have basically a flame retardant outfit that I had purchased at one point in my closet when I actually had to visit some of these sites. So I got some firsthand experience seeing a lot of this equipment in operation with Morningstar controllers installed beside them. So it's definitely quite an interesting application and one that's been around for a long time. The oil and gas industry was one of the earliest adopters of off-grid solar power back in the early days. So excited to talk about it today. So first, a little bit about Morningstar. We think of ourselves as the charging experts with over 4 million products deployed since our inception in 1993. We sell globally through a variety of distributors around the world in over 100 countries, and a lot of the reliability comes from the fact that we've got the lowest hardware failure rate in the industry, and that's why we believe our customers continue to rely on us as the go-to standard for these types of applications. A lot of the industries that we focus on are industrial solar, which covers both telecommunications, oil, gas, security, and some lighting applications. We do commercial work as well. The mobile and marine industry, a big user of renewable energy, of course, as well as agricultural. And we do also support residential or home-based systems, as well as rural electrification. And these would be off-grid solar systems in non-electrified regions of areas such as South America, Africa, and other parts of the world. A notable project that we worked on in a couple of years ago was actually a deployment of off-grid solar home systems in Peru, and that was in partnership with Tozy Green and the government of Peru, and we deployed power systems for over 200,000 homes and 3,000 community centers, so providing power to a previously unelectrified region that supported 1 million people. So we're particularly proud about that type of work. Okay, next slide. So as I had mentioned earlier, the oil and gas application is one that has relied on solar for some time. And when you look at why they adopted it so quickly, obviously the cost per watt of solar panels many years, even multiple decades back, was quite a bit higher. And that's because it got the job done. It was a very remote system. We have pipelines traversing the desert. Solar provides the lowest operating costs or expenditure of any remote power solution. And when you compare it to the mechanical requirements that you see with wind, or of course fossil fuel burning generators or other applications that require fuel and servicing needs, it's really just extremely reliable because of all that it has to offer, and minimal parts to fail, no field maintenance really required. The long battery lives that are coming from proper battery charging, as well as transition to lithium batteries that have an even longer life, all around, it just has a variety of benefits. And it also helps achieve, some of the environmental applications and initiatives that are also sought after by the oil and gas industry, by using renewable energy to power and monitor remotely their petroleum and gas products. So all around, it's an excellent industry to be a part of. Next slide. So in terms of where we fit in the applications, there's kind of three main components of the industry: upstream, midstream, and downstream. In this present application we're talking about today, we're really focused on upstream and midstream. So upstream would be, of course, the actual collection of the fuel itself from wells, and in some cases from offshore applications, where they're actually doing the exploratory work and actually getting the fuel out of the ground or in the ocean in some cases. In midstream, it's much more about processes and automation control that takes place in order to transport, to measure, to process, to collect, and basically get those fossil fuels from their locations at the site of the well actually into the refining process and ready for transport. So there's a variety of applications in those two segments of the industry that we work with quite heavily. Next slide. And some of the loads that actually get powered in those applications are extremely diverse. And we kind of break those into two sections. On the small and medium power, what you'll see are RTUs, PLCs. Those are basically data collection and measurement devices. Human machine interfaces are displays or informational, information that's given to the user or to a remote management site in order to ascertain what's happening at the site. There's a variety of wireless interface and IO that's happening at the site so that they can get temperature, pressures, measure the level of tanks, the flow of gas or petroleum through a pipeline. All of this is very expensive assets and ones that have to be monitored very carefully, not only for the monetary aspects and the asset control, but also for safety. And in some cases, even actuators and solenoids can be used to actually change flow and manage these automation processes. And then security cameras are also becoming a big part, especially with 4G and 5G applications, where they can actually get eyes on the site even from a great distance. So those are pretty typical on the low power side and easily powered by solar applications. On the larger side, you'll see a lot of bigger applications, some that are more power intensive, but also very capable to be powered by solar applications. In that case, we see some of our larger products used, and that would be more energy intensive processes such as cathodic protection, which handles the inhibition of rust, injection valves that are actually putting methanol and other chemicals into the pipeline to prevent freeze-ups and provide treatment processes, pumps, motors, and a lot of times even backup power applications can have solar added to them along the way. Next slide. So what we'll be talking a little bit about today are these specific certifications that are applied, and we've got several new certs that have been applied to a variety of our products in our portfolio, and that's what I'll be covering today. So just a quick overview, UL and CSA are long understood as standards for safety, as well as a variety of other certifications for products, and those cover the North American markets. And what we're also seeing is that we've added global support, in some cases for the greater portions of the globe, with international coverage with IECEx, and then specifically with a focus on the European Union countries, we have ATEX. So those four certifications make up a lot of the listings that have been applied to our products and allow them to be used in these hazardous applications. Okay, and I'll be covering those in a little bit more detail. What should be understood with these is these are a lot of times a lab as well as a certification. For instance, UL and CSA have their own certifications, some of which are on our products, but there's a variety of nationally recognized testing laboratories that can actually test to these standards besides just these labs alone. Other examples being TUV, ETL, and others internationally. Okay, so that makes up the four that we'll be discussing. Next slide, please. So as you can see here in our product line, there's a lot of changes as indicated by the new badge there next to several of our products. And you can see that the ProStar MPPT and the ProStar PWM have all of these markings, as well as the Sunsaver MPPT. So you'll know probably and be very familiar with the Sunsaver PWM and the Sunkeeper, which have long been part of this portfolio, but a lot of our larger capacity PWM and MPPT controllers have been added to also have these listings. So you can see there, as indicated by the diagram, the EX and IECEx certifications, as well as the ETL listing for HasLock has been added to a variety of our MPPT controllers, which is a pretty big change, and it's going to offer a lot of new capabilities in terms of PowerPoint tracking, which many customers have asked for, as well as several other features. And below, what that actually details is for some that want the very specific details of these listings, the requirement of the lab is that we actually put these markings on the product so that someone who's installing it can actually see written on the unit itself where exactly they can be used. And if you'd like to take some time outside of the webinar, you can actually see what each of these denotions means in the description. And it relates to the gas that can be used, the temperature ratings, the type of environment. It's very specific, and I'll be talking about that shortly. Okay, next slide. So what a hazardous area classification really covers, to break it down, is there's summed up, there's two types of environments that we're talking about. Okay, a division one, first of all, the class we're talking about is gas, vapors, and liquids, which covers most of these applications. Division one is an area where it is normally explosive and hazardous, such as something that was operating inside of a tank where it's exposed to this environment all the time. It is assumed that it is surrounded by an explosive gas. What Morningstar's products are rated for is Division 2, which means that they are near to that application. They are not normally present in an explosive concentration, but that type of environment could exist if there was a leak or a malfunction, and therefore the product needs to be designed safely and certified correctly so that if that occurrence did happen, that the product would not, contribute to an explosion. So that Division 2, or as I said, Class 1 Division 2 is what these products are actually listed for. And then the groups cover the different types of gases that actually may be present. On the right, you'll also see that across the listings that we have, there is a zone system as well, which is similar but differs somewhat from the Division 2 application, and that Zone 2 is also something that is normally not exposed to these types of concentrations of explosive gas, but could occur. And those are the differences covered between the North American certifications and the international ones. Okay, next slide, please. So what's new? What we'd like to talk about is kind of a simplified diagram here to really give a clear explanation of what our products have gone through in terms of changes and what new products now have these certifications. Okay, so in terms of UL and CSA listing for both the United States and for Canada, the ETL listing for Class 1 Division 2 has now been applied to cover not only the Sunsaver and Sunkeeper seen before, but also the ProStar MPPT, and Sunsaver MPPT. So you now have much greater capacity as well as maximum PowerPoint tracking options that can be used within these zones. In addition to that, the Sunsaver and ProStar PPT and PWM, as well as Sunsaver MPPT, have also gained the additional global acceptance of having the IECEx and ATEX certifications. So your applications in possibly Asia or other parts of the Middle East now have that coverage with IEC, and specifically within the European Union, the ATEX certification is preferred. So we now cover all of those applications, increasing our global presence in this industry. Next slide. So what this also provides in terms of benefits, besides just these models, is you'll now see some really unique features from a technical standpoint. The first being, of course, you've got MPPT, so you have more power available with the boosting capabilities, as well as the fact that the ProStar MPPT and PWM are just larger capacity. Our Sunsaver previously reached a maximum current rating of 20 amps at 24 volts, whereas the ProStar gets up to 30 amps. And in the case of the MPPT ProStar, we have both 25 and 40 amp models available. And that gives a lot of increased capacity to power generally larger systems, especially at 24 volts, which we see is really becoming a standard in this industry. Also, you gain the ability to actually oversize the array. PWM controllers much operate at a maximum current level, but MPPT can be oversized, very similar to how grid tie inverters are often designed for 120 or 130% over their capacity because they will automatically current limit. So that gives a lot of additional reliability in terms of the sizing. Lighting control is also an option in these products, and we've seen a lot of lighting applications for safety at these sites as well. And also you now have products that offer an optional meter that can be placed inside the product, or I'm sorry, is placed inside the product on certain M models, so that a meter display as well as adjustability of the set points can now be achieved in these zones. Next slide, please. Lastly, we have communications options. All three of these products that have gained this listing also have our standard meter bus interface that can provide communications with other Morningstar accessories, as well as communicate via standard Modbus or even SNMP, so that you can do remote monitoring. You can interface with a lot of the SCADA equipment that's at the site, and you can access this data remotely in order to determine what the performance of the system is. So data was not previously available on the smaller Sunsaver line. Therefore, this is a big change that we think will really contribute to increased adoption, especially during some of these developments that are taking place in digital oil field deployments. Next slide. So one of the things that to kind of further discuss that data accessibility, we have a lot of products that support the data connectivity as well as these accessories, one of which is the EMC1, which provides Modbus over IP for Ethernet enabled sites, which is becoming very common, and also SNMP. And a lot of this equipment can then be used with remote connectivity, such as satellite connections, private LTE networks, cellular, and these network management systems, such as those provided for SNMP by companies such as Zabbix, or Modbus applications run by cloud HMI systems, can use SCADA monitoring to actually log data from these equipment from the equipment remotely. So we see that a big benefit for integrating into basically an entire system monitoring view of what this equipment is actually doing. And it's also going alongside data logging that's already in place for oil and gas process applications. So two different needs, petroleum access as well as power access, similar interface. So it's really bring things together quite nicely. Next slide. So just to summarize here with the products, the Sunsaver has gained additional functionality with, an application support with the EX and IECEx, as well as the ProStar and ProStar MPPT and Sunsaver MPPT. So these four products really cover the majority of our mid to low power range systems, and now are all available for these three global standards. Next slide. And one final thing to note, if you're familiar with Morningstar's products and a lot of the accessories that can be used, such as data communication bridges and accessories to communicate with other serial devices or RS-45 buses, these products, while not uniquely listed themselves as a standalone product, can be used with the equivalent controller that I just previously spoke about on the last slide, together as a system in these environments. So in other words, these products have gone through the listing process and are part of the test report that actually has to be processed by Morningstar in order to get these listings. So products that drive relays, such as the relay driver, or provide remote IP connectivity, such as the EMC1, have gone through this listing process with the host controller. So when the solar controller and these accessories are used together, they do comply with the listing requirements and can also be used in these applications, which is a pretty critical need because of the need for data. Okay, next slide. Okay, so with that, I will now introduce Errol from SunWise Power and Battery, and he can take it away and talk more about the system applications and more in depth with how some of Morningstar's products are integrated. Okay, thanks very much. Take it away, Errol.
Thank you very much, Brad. Really appreciate it. Great presentation. And so, yeah, we're going to start off here with a little polling question, and then I'll get into my section. And what we covered so far may not immediately be intuitive to people as relating to battery longevity or health, but as we'll see in some of the rest of the presentation, they are actually closely related. So I'm going to go ahead and launch a polling question. Hopefully everybody sees those polling options. All right, I'm starting to see some votes come in. Please go ahead and give us some feedback on what approximate longevity you guys are usually experiencing with your batteries. I think kind of the assumption here is that we're talking about lead acid, but if you're getting more than 6 years, either you're doing something great or you might be using a different chemistry. So I think about 53% of people have voted. Give it another 10 or 15 seconds, let a few more people get their feedback in. All right, looks like we got some good responses back. I'll go ahead and close the poll. Okay, there. And everybody see the results up. Looks like about more than 40% indicated they're getting less than 4 years, with another 40% indicating they're getting approximately 4 to 6 years. So thank you very much for that feedback. Appreciate it. Okay, so as Brad mentioned, my name is Errol Rankin, VP Sales and Technologies over here at SunWise Power and Battery. Similar to Morningstar, we actually got our start around 1993 as well, and both of our companies have actually been working pretty closely since not too long after that. We pretty much exclusively focus on off-grid industrial power solutions, and primarily on the left-hand side, you'll see the turnkey system offerings that we focus on. That includes standalone PV, as well as battery backup systems and hybrid solutions that include wind generators, thermoelectric generators, fuel cell technologies, mobile power systems, control panels, subassemblies, kits, and other value-added solutions. And on the right-hand side, in terms of components that we sell to our partners, they're essentially the components that make up our turnkey systems. And so that includes solar modules, Class 1 Division 2 solar modules, Morningstar charge controllers, solar mounts, enclosures, many other components. And we also have a web store presence with easy online ordering and dealer pricing available. So a quick overview, again, on the left, we've got kind of turnkey solar PV systems, standalone. In the middle, we've got our power station and our hybrid lines that scale up typically with the size of the loads. And then on the right, some examples for battery backup and AC input loads, as well as a tech note link on the bottom in case you want to read some more white paper information about these type of turnkey systems. So SunWise has a presence on both the East and the West Coast in terms of manufacturing, warehousing, and fulfillment. We serve all of North America proper, and you can find lots of good video content on our YouTube page, as well as some of the additional services that we offer listed over on the right-hand side. So I want to briefly cover what is a standalone PV system, and I'll cover the 3 components highlighted in green, since this is some areas where we have a lot of proprietary manufacturing involvement. And then of course we covered the solar charge controllers, and batteries themselves are usually such a large topic that I think that warrants a standalone discussion. And then at the end, we have optional AC, DC, or hybrid components. So if power regulation equipment is required, or something that may be optional but not required for standard DC loads, those may be incorporated as well. In terms of size, generally we're talking about, for standalone systems, running loads that are approximately between 1 watts to 200 watts continuous. Okay, so talking about solar modules briefly, this is a very obviously important part of the solar system. They're especially so for HAZLOC and Class 1 Division 2 applications, because they are one of the components that also carry the same Class 1 Division 2 certification. So we'll be talking about that a little bit, but I do just briefly want to go over some of the core definitions around a solar module. Lots of this information and more can be found on the TechNote link at the top of the slide. So for solar modules, especially rigid glass and aluminum solar modules, we're typically talking about what's called nominal 12 volt, which is actually 36 cell, or nominal 24 volt, which is typically 72 cell. And those are going to be the majority of the Class 1 Division 2 solar modules that are available for these types of applications. And then of course, there's lots of other variations. There's 60 cell solar modules. There are now half-cut 144 cell and PERC modules, as well as bifacial and other designs. There's also non-glass modules, either featuring epoxy resins or other types of laminates, and you can see an example picture of that over on the right-hand side. As Brad alluded to, in the Class 1 Division 2 group classifications, we have these A, B, C, D groups. And so one thing that I'll point out about that as it relates to solar modules on the next slide, but before I do that, at the bottom, you'll see here some rough capacity ratings for commonly available Class 1 Division 2 solar modules. Now, different manufacturers, different distributors may have, slightly different variations, but this gives you a feeling for what types of module ratings can be ordered with a Class 1 Division 2 certification, either as a nominal 12 volt or a nominal 24 volt. You'll see the biggest difference is a little bit less granularity at 24 volt because nominal 24 volt C1D2 modules are a little bit less common, and they also don't go down quite as small to some of those 5 or 10 watt rating capacities. So some of the design considerations that we want to be thinking about when it comes to solar modules and array, now that we have MPPT and C1D2 charge controllers, is the fact that the MPPT technology in these base devices allow for higher voltage array stringing due to that maximum open circuit voltage on the charge controller. It also is going to future-proof some of your designs a little bit by supporting in the future these higher rated capacity solar modules, which are always growing in size due to cell efficiency increases in the marketplace and from manufacturers. And then as Brad alluded to, having an MPPT charge controller is now going to give us the ability to oversize our arrays, which is not only going to improve performance during certain low sunlight conditions, but it's also going to help improve our battery life by getting that extra power production and keeping them on average at a higher state of charge. And then lastly, the flexibility to string our arrays at higher voltages than our battery bank is going to give us the ability in some cases to save on balance of system costs, potentially reduce inventory management by stocking a smaller number of control panels or charge controllers and not having to worry about that 12, 24 volt breakout, as well as giving you more power. All right, so as I was mentioning, in the solar module, the label, similar to the charge controllers, is it's basically mandated by these authorizing bodies that it contains any certification information. So there's a wealth of info that you can find on a solar module label. And in addition to all the great core details around, electrical parameters and series fuse ratings and so forth, I did want to point out that within this group classification, it's not a given that just because a solar module is certified to Class 1 Division 2, that it is so for all groups A, B, C, D. So just as an example on the left for the SolarTech Power SPM 085P, that solar module is actually only certified to group C and D. And they have other modules that are only certified to group C and D, whereas other modules of theirs, as well as all the SunWise C1D2 solar modules, are certified to groups A, B, C, D. So it's a small detail and note to be mindful of depending on what exact group zone you're actually going to be installing these in. Another thing I want to point out about solar modules is this junction box configuration, which is pretty much the standard for all Class 1 Division 2 solar modules. On the left, you'll see an example of a solar module with an MC4 factory installed junction box. While those are very common, I'm not aware of any Class 1 Division 2 solar modules that have that. Typically, a Class 1 Division 2 solar module is going to require a junction box as shown in the middle picture. So that's going to have an exposed area for us to wire and work with the terminal bus bars and the bypass diodes. And so if you're not familiar with how to wire a junction box, that's going to be an important component of working with these Class 1 Division 2 solar modules. And so you can see a picture on the right after everything has been installed, including the knockouts and the cord grips and the wires terminated on the right bus bars. What does that look like? Moving on to the next category, really quickly, we're going to be talking about solar mounts. These are required to support structurally the solar modules. We have a tech note at the top. I just want to point out a couple things. As an example, using a Class 1 Division 2 certified 195 watt solar module, you can see the rough quantity allowable on each one of these standard designs. So a side pole mount is going to support up to 4 of these modules. Our skid mounts currently would support up to 3 of them. A top of pole configuration would support up to 12. A ground mount would support up to 4, but would be modular. And then our proprietary SunWise power station frame will actually support up to 20 Class 1 Division 2 solar modules for about a 4 kilowatt array. And when thinking about solar mounts, one of the main design considerations you want to keep in mind is wind speed ratings if you are working in a high wind speed area. And so those are typically rated between 90 and 130 miles an hour or more, and is dependent on a couple site installation criteria such as tilt angle, height of the installation, as well as snow load. Here's just a quick diagram overview that shows roughly the range of supported array sizes for these different types of mounting solutions. All right, and the last category that we're going to talk about really quickly is enclosures. And so enclosures primarily are there to protect the controls equipment as well as the batteries from any sort of exposure to the outside conditions. All of the SunWise enclosures are NEMA 3R rated for outdoor use, and their core purpose is to be able to allow both that controls equipment and the battery to be stored in one simple accessible location. Sizes can range anywhere from supporting about 7 amp hours at 12 volts to 3000 amp hours at 48 volts. These are common for our applications, or equivalent to about 0.1 kilowatt hours to 144 kilowatt hours. Here's an example on the left. That's a dedicated energy storage housing. That's a Unity battery bank of about 3000 amp hours at 48 volts or 144 kilowatt hours. And then on the right, you'll see a real common example for a single battery pole mounted enclosure with a ProStar PWM along with all the other control circuitry. A couple more examples of the different flavors and formats of enclosures that you might see. And this is going to come into the play in the presentation as we start to talk about the design architecture of these larger systems and loads as they grow in size. Okay, so with that brief overview about the core system components out of the way, I want to talk really quickly about a real world example for what we've been discussing so far. So this is a project that SunWise built in 2018 for one of our clients. The application was for powering a 15-watt continuous load for a flow meter. That flow meter ran off of a DC voltage range of 23 to 32 volts, which we'll talk about in a moment. The location was for Louisville, Kentucky, and you'll see here there's 2 key design parameters that I'm going to touch on, what we call an ALR, that's an array to load ratio of 1.33, as well as 5.1 days of battery autonomy or battery backup. And then there's going to be 3 major components within this system that contain Class 1 Division 2 certifications. And so that's going to be the solar module, which we just discussed. In this case, we're using a 150 watt nominal 12 volt wired in series Class 1 Division 2 solar module. And we used in this case the Sunsaver 20L 24 volt C1D2 controller and C1D2 certified breakers for the control panel. One thing I want to point out on this slide is that for the purposes of today's discussion, and really in the majority or the vast majority of the HAZLOG or C1D2 applications that SunWise services, we're usually talking about a system or an assembly with Class 1 Division 2 components. Now, that is different than a system or assembly that is Class 1 Division 2 certified at the system assembly level. Both of those things exist, they're both applicable, but primarily we're going to be talking about a series of components whereby the major components have this Class 1 Division 2 certification, and that's often the design solution that we actually see out in the field, not a C1D2 certified system. Okay, so what is the bill of material for this application that's supporting a 15-watt load in Louisville, Kentucky? So as we mentioned, we've got our 250-watt solar modules. In this case, we upgraded to 160-watt due to inventory availability at the time of order. That's not an uncommon occurrence. Therefore, we like to design conservatively around the 150-watt. Therefore, we know if and when we have to sub for 160, we'll be fine. On the mount, you'll see we've got a standard side of pole mount. It supports 2 of these solar modules. We've got our output cable and conduit for sun protection, about 15 feet to bring us from the array to the charge controller. We've got our enclosure specification. In this case, it's a SunWise WF2. We've got our 2 MK Deca 8G38 gel batteries. And then we've got our Sunsaver 20L 24-volt charge controller, as well as our 3 C1 D2 breakers. These ones are actually C1 D1. They're both C1 D1 and C1 D2, and those are rated for 20 amp. So here's a layout image of this example system in question. So we've got our 2 solar modules, we've got our side of pole array, we've got our pole mounted enclosure, and now we have our front view of the enclosure. We've got our 2 batteries wired in series for 24 volts. And you'll notice here, this enclosure that was chosen, the WF2, it's focused on extra space on the backplate for customer equipment. And so this is all space that's available for the customer to integrate their own load equipment that the system is powering. So very common system, very straightforward design for these types of oil and gas applications. Now, I want to talk a little bit about the design overview on this slide and highlight a couple things for people's attention. So the first one I want to talk about is this comment on the top left about this NREL 93821. So the first thing is that, not all solar resource data is equal. And the reliability of the system design is only going to be as good as our design assumptions. Therefore, SunWise prefers real-world ground-based data, typically available through NREL or the National Solar Radiation Database, NSRDB, or others. So be mindful and try to avoid geospatial solar data if possible. It's not always avoidable. And remember to use worst-case month solar data if your system's going to be operating year-round. And of course, working with an expert can be very helpful because not a lot of businesses have their core expertise as off-grid solar design. This lets them focus on their core competencies. The other thing I want to point out is that note that the design load we list in amp hours per day, that's very convenient for a number of reasons. It lets us combine loads at different voltages and get one unified number. It also allows us to do back of the envelope calculations around autonomy really quickly and easily. So if we know we have a 100 amp hour battery bank and a 20 amp hour load, we can know in our head that we've got a 5-day backup design for that system. All right, so now looking at things on a monthly level for this design, you'll notice kind of moving from the columns left to right. On the first column, this is the array insolation hitting the array. We've got our average monthly temperatures. And then going to the third column, we've got our energy production from the array on amp hours per day. That's an average value in a given calendar month. And we've got our system losses assumed at 10%. We've got our consistent load at 15 amp hours per day. And then in the last right 2 columns, you'll see our battery size that I alluded to. So in December, the worst case month, we've got at least 5.1 days of autonomy, and we've got an array to load ratio of 1.33. And again, we'll talk about this a little bit more in some of the next slides. The array to load ratio is essentially the ratio of energy produced by the solar array to the energy consumed by the load. It's essentially a safety factor or a design factor on the solar array side of things. We want that to be somewhere in the 1.2 to 1.4 range. All right, looking at this is what's called a battery waterfall chart, and it shows the estimated percent of time that the battery will spend in each given state of charge bracket for a given month. So what ruins batteries, going back to this poll question that we had about how long your batteries last, what ruins batteries is remaining in low, what ruins lead acid batteries is remaining in low states of charge for prolonged periods of time. So a 20% state of charge or an 80% depth of discharge is the typical cutoff LVD, which is why this chart ends at the 20 to 28%. Therefore, any time spent below that would be considered a low voltage disconnect or a load failure. And if you're thinking, well, can I raise my LVD set points to potentially increase the life of my batteries and prevent the time that it spends at these low state of charge, yes, that is a valid design approach that you could take. So just to recap these two core design parameters, ALR and battery autonomy, visually, you can see on the top, the blue horizontal line is our normalized system load baseline, which is always 1. And then you can see the array to load ratio over the course of the year. December for us in North America is typically our worst solar resource month. And so that's the one that we design around. And that's where you can see the 1.33 ALR. And then on the battery waterfall, you can see on average, we're never dropping below 90% state of charge on average over the course of a month. And now we've got a pretty simple line diagram basically showing the solar charge controller as well as the 3 different breakers for solar array, battery, and load. This system uses class 1 division 2 breakers as we noted. However, if it's not desired or needed, you can use class 1 division 2 fuses and fuse holders to save a little money, but it does make maintenance and troubleshooting a little bit less convenient. All right, so as we talked about, I want to point people to IEEE 1562 if you're not aware of it. We have a tech note on this topic. It is the only published standard for off-grid system design that exists. And so if you reference this, you'll see that's where we're pulling this 5 to 7 days of battery backup. That's kind of the sweet spot for system design. And then similarly for the ALR, this 1.3 to 1.4. And what we've seen at SunWise is over the years, as the cost of solar has continued to plummet, it has been very convenient for us to raise the ALR because it costs little to nothing to add some of these higher capacity modules and draw back a little bit on the autonomy, at least for dry climates or non-critical loads. And that's giving us equivalent levels of reliability for a little bit less cost. Okay, so now we're going to be moving on from a specific real world example, and we're going to be talking a little bit about this future design architecture around these new Morningstar charge controllers, particularly the ProStar 30 and the ProStar 40 MPPT, since those are the higher current rated capacity charge controllers to have this new Class 1 Division 2 certification. So looking at this chart, on the y-axis, we have the average continuous load in watts that is supported by each one of these charge controllers. No surprise that going from a Sunsaver 20, we're approximately doubling our continuous load going to a ProStar 40 amp. Now you'll see I've got a couple asterisks here, and it's a little bit perhaps counterintuitive what we're doing, but this is done very purposefully, as this is actually the design philosophy that SunWise uses. So what we've done here is we've actually modeled the ProStar 40 MPPT as a PWM. So we're really treating this as a 40 amp PWM charge controller, and we're saying this is the load it could support if it was a PWM. Now, this is the load that our design modeling software says it could support treating as an MPPT. We believe that's a little bit, it overestimates the production in our opinion, and we like to keep that conservative. And so in a real world, what we think the proper load estimate range is for this ProStar 40 MPPT is somewhere between this 60 and 70 watt continuous range, depending on the exact conditions. And this would of course be dependent on the solar resources of the site in question. For our purposes here in this example, I've used Midland, Texas. And so this is what we're going to be talking a little bit about, what happens with these designs as they grow into these larger loads. Okay, so we're going to start with 12 volt system architecture. And these are our design parameters. So the first design parameter is that the load is going to be able to operate off the nominal DC voltage range of the 12 volt battery bank. So basically your equipment needs to be okay to run on a DC voltage range of 11.5 to 16 volts. The second one is that we've set the low voltage disconnect for the batteries at 80% standard. The design performance for the purposes of solar array modeling was kept from negative 20C to 40C, and I'll speak a little bit more about what that means. But in terms of component ratings, everything's rated up to 60C, and so the system will function no problem up to 60C in this case. And then of course, we've got some specific array to load ratios per the design standards that we just talked about. We're keeping the autonomy at a minimum of 5 to 7 days, and we're ensuring a very reliable system design of 99.99% estimated uptime. So what we're gonna cover is what loads can you now run in these HAZLOC locations, and what does that system architecture look like? And what are some of the implications along the way? Okay. So looking at these three controllers for a 12-volt system, Midland, Texas, you've got the Sunsaver 20L 12 volt on the left-hand side, and we're saying that's going to run at maximum about a 29-watt continuous load. And going through what that system is, it's about a 360-watt array using 280-watt solar modules. It's got a 530 amp hour battery bank for 7.7 days of autonomy, which is a little bit on the high end. And then you'll see the array is either going to be side-of-pole or skid mounted with a side-of-pole enclosure. Moving on to the ProStar PWM, we've now got a 1.4 ALR, 540 watt array, 5.1 days of backup with a 530 amp hour battery, side-of-pole skid array, side-of-pole enclosure, now supporting a 43.5 watt load. And then moving on to the ProStar MPPT, now we're moving up to a 585 watt array, 5 days backup, 660 amp hour battery, same array and enclosure configuration. And now, due to this question around how much extra power production should we really allocate to that MPPT technology, we're giving that load range as 55 to 70 watts, which I'll talk about a little bit more. So the first thing I want to mention is that when going through each one of these examples, and also SunWise in our day-to-day, we use the Morningstar string sizing tool, which is a great product. It's available under their products drop-down. They have a tremendous database of solar modules available. And so it makes it really easy to go in here, choose your specific solar module, your temperature profile, and your charge controller, and figure out what exactly the manufacturer recommendations are for your upper limits on array stringing options. So in this case, you can see our 280 watt solar modules for 360 watt is the preferred optimal array configuration for this. So here's just a quick recap of the 12 volt systems that we talked about. Namely, at the bottom, you'll see here that the first two systems are using the MK Deca 8G8D batteries. But as the load goes up for that third system at 55 watts, we're having to make a couple adjustments in order to get that minimum 5 days of autonomy, namely going from the 8G8D up to the EV330 battery, which is going to give us quite a bit more capacity on a per battery basis using the same form factor. So what I want to highlight to folks is this reduction in dollars per continuous watts of load. Starting with a Sunsaver 20L 12 volt, we started at $120 per continuous watt of runtime. And moving up to the ProStar 40 MPPT, that's dropped all the way down to $79 per watt. So a really significant reduction just due to the simple economy of scale of the entire completed system. Okay, so visually, what does this look like? So on the left-hand side, you'll see we've got our side-of-pole mount array, we've got our 280 watt solar modules, our pole-mounted enclosure, front opening, you can see our two 8G8D batteries along with our Sunsaver charge controller. Moving on to the next design, we've now got 3 solar modules. We've moved to a skid format in order to save a little bit on the foundation and installation costs because no poles now going to be required. We're keeping the same enclosure and the same battery configuration, and now we've got our ProStar 30 charge controller. Now moving to the third system, you'll see in order to support these higher loads, we're having to do a couple tweaks, but overall keep the same form factor. We're going to change these 180 watt modules out for 195 watt modules to give us a little bit larger array. And we're going to switch out these 265 amp hour capacity batteries with these 330 amp hour capacity AGMs in order to make the design criteria work per those ALR and battery autonomy requirements that we set for ourselves. Okay, so now we're going to go through the same exercise at 24 volts. So you can see just due to the jump in DC voltage on the charge controller ratings, they inherently support essentially twice the array, thus twice the load because of that doubling in the voltage rating. So very similar chart, but ultimately higher values. And you can see our upper load estimate range for 24 volt PS 40 MPPT is now in the 120 to 140 watt range. So our design criteria again is going to be exactly the same, except now our load equipment needs to be able to run off of that 23 to 32 volt DC window instead. Okay, so highlighting some of the changes from the 12 volt to the 24 volt configuration in red, you'll see that the array doubled going from 12 volt to 24 volt. Therefore, our load doubled, but our battery capacity also doubled, and therefore our enclosure solution needs to move from a pole mount to a ground mount in a different design. Similarly, on the ProStar PWM, we're moving from a 3 mod array to a 6 mod array, which is going to push us up to a different style array for a top of pole format. And then also these both go to ground enclosures and the array doubles in size. So here is the same breakdown for the 24 volt systems with the Sunsaver 20L on the first column, the ProStar 30M PWM in the middle column, and the ProStar 40 MPPT on the right-hand column. So notice that our enclosure design has now moved over to this T4x8D ground style enclosure to handle 4 of the 8D batteries, and we've moved over to a larger array mounting in all of these. And importantly, we've dropped now from a Sunsaver at $112 per watt all the way down to $70 per watt. And this $70 per watt is not assuming any benefit of extra MPPT energy production, which I will touch on in the coming slides here in more detail. Okay, so visually, what do these 24 volt systems look like? Well, we have a side of pole mount array, and we've got 4 of our 180 watt modules, and then we've got our chest style enclosure on the bottom with 4 of our Group 8D batteries wired 2 in series, 2 in parallel for 24 volts. And then you can see our Sunsaver control panel is going to mount over here on the left-hand side of the enclosure. Okay. Moving up to the system using the ProStar 30 at 24 volts, we're now moving to a top of pole mount array, which features 6 modules, and then same enclosure, same batteries, but now we're going to the ProStar PWM on the control panel. And then for the ProStar 40 MPPT example, we're going to be similarly swapping out the modules for the 195 watt modules and the 265 amp hour batteries for the 330 amp hour batteries. And that's going to give us the ALR and the autonomy that we need to support this 110 watt load. So in summary, going from our Sunsaver 12 volt 20L design, we supported a 29 watt load, and it cost us about $120 per watt of continuous load supported. Now moving up to a C1D2 24 volt ProStar 40 amp MPPT, we're now up supporting at the upper end of our comfort limit with an MPPT, 130 watt load, or coming all the way down to $59 per watt continuous, or a more than half reduction in the overall cost per watt of supporting a Class 1 Division 2 system for a HAZLOC load. So this just really summarizes, at least at 24 volts, the reduction in dollars per watt of continuous load operation for these systems. And now I want to talk just really briefly about what can be done immediately for some of these new product options. So obviously we covered what does some of the future design architecture look like moving forward with these new Class 1 Division 2 charge controllers, but what are some of the things that you could potentially do as an operator of existing systems out in the field right now? Well, the first thing that you could do is you could replace a PWM C1D2 charge controller with a MPPT C1D2 charge controller. And right off the bat, that's just going to significantly increase the power production from your array, increase the reliability of the system, as well as increasing the battery life by making sure they remain at higher states of charge. You could now potentially replace your VRLA batteries with lithium iron phosphate or other lithium batteries now that we have custom programmable set points as a feature in these new charge controllers, potentially increasing the total lifetime of your system by 3 to 5 years. We could now add remote monitoring to include predictive maintenance and data for the health of the system. We could now, with the larger rated solar charge controllers, augment or retrofit solar systems with additional solar, and that can increase the reliability of the system or allow us to increase loads. We could incorporate an onboard meter, which allows for easier on-site analysis for maintenance workers to troubleshoot systems and understand how they're performing. We could improve temperature control by customizing compensation set points within the charge controller. And we could add remote control via a relay driver for contactor opening and closing and other sort of advanced remote control functionality. And of course, you can ask SunWise for additional guidance on retrofit options. And so in summary, to encapsulate what we talked about today, the larger charge controllers from Morningstar that have these new HazLock features and capabilities are now rated for not just North America, but Europe and other parts of the world as well. And these new developments can benefit not only new system designs, but also retrofits at existing offshore and onshore upstream and midstream oil and gas sites and other HazLock zones, such as mining, chemicals, etc. And as we talked about, Morningstar and SunWise has had a close partnership for several decades, working with customers and clients like yourselves to deliver reliable remote power solutions for oil and gas sites and other applications. So with that said, we have a few more minutes left, and I think, Mark, we would like to open it up to questions at this time.
Sure. I just want to test, can you hear my audio okay?
I can hear you fine, Mark.
Perfect. Great. Yeah, we did have some questions come in. The first one, there's a couple questions by Tushar and some others that relate to Underwriter Laboratories. So I guess this is probably a question for Brad, because I think he's gotten this question a number of times. But basically the question here is, do the controllers have to be tested by UL Labs, or is ETL or other labs sufficient? And can you just kind of go over that, like which is better, or are they the same?
Sure. Yeah, I mean, there's two things to think about here. One is, what is the actual certification or listing? In this case, we're talking Class 1 Division 2. A more standard safety version might be UL 1741 is the famous one used in the solar industry. And that standard is defined in terms of by a panel and in conjunction with a lab in order to define what those standards are, with lots of contribution from the industry. Once that is defined, it becomes the process, and the testing and the listing requirements are all part and parcel with getting that listing, and it has to be tested to that standard. Who actually does the testing does not actually have to be the lab that actually wrote the standard. In other words, a UL 1741 or a Class 1 Division 2 standard could be written by UL, and it could also be tested by UL, but it could also be written by UL and tested by ETL, TUV, Factory Mutual, other types of international IEC locations. So the summary is that the lab itself does not have to be the lab that actually wrote the standard in order to do the testing, although usually one of them is the key contributor or author of the standard itself. Okay, I hope that's clear.
Very clear. Thanks for that question. Thanks for the answer. All right, another question. Let's see. To use one of these products and maintain the listing, is there a particular installation practice and parts to be used, like certain solar modules, certain batteries, certain breakers, etc.? And I think you touched upon this, Errol, so I'll pose this question for you if you can take that.
Yeah, sure. So this is a good, interesting question. I believe the component level certification in most cases is independent of the configuration in which it is used or the other auxiliary devices around it. Now, Brad, does that jive with your understanding as well, in that, like, if you put a Sunsaver that's class 1 division 2 in a certain location, in a certain application, there's nothing really you can do around it that would take away the class 1 division 2 certification rating of that Sunsaver component? Does that jive with your understanding?
Yeah, I would say generally the key areas of focus are the modules, which you clearly
Mm-hmm.
covered, the controller being the main power conversion device,
Mm-hmm.
sometimes some of the safety equipment such as breakers, things that switch,
Mm-hmm.
actuate, connect, disconnect. Batteries are generally excluded from that. They're
Mm-hmm.
pretty standard in operation, and that's about
Mm-hmm.
it. Those are most of the core components that are required.
Yeah, and this actually touches on a different question from Jeff Warren in chat as well, where he's just asking specifically about the comment that I mentioned regarding uh, uh, system that uses class 1 division 2 certified components versus something that is certified at the system assembly level. And so to relay off of what Brad was mentioning, for most of our applications, when we're selling systems with class 1 division 2 certified components, it's the solar module, the solar charge controller, and the breakers or the fuses that are typically covered by that. But that is a very core basic system without really any other major components. So the wire we pretty much ignore, the battery we pretty much ignore, the terminal blocks and other small things like that we pretty much ignore. And that seems to work well for most installers and most applications. So those are the major components that you would want to keep certified in order to keep this overall system architecture in line with common industry practice. Now, that's my perspective. Now, Jeff, to your question, he asked about the pros and the cons of a C1D2 certified versus a collection of C1D2 certified components. And so I have two comments with regards to this. So the first one is that if you can get away with using just C1D2 components, then do that, I think, and that's what most people do. And so that's really dependent on what level of regulatory control is your application facing. So, if you're out on private land in oil and gas development, again, if you want to kind of blow yourself up, who's really going to stop you? Whereas there's other applications where it's much more heavily regulated. And so the question of requiring C1D2 components versus C1D2 system, I would say, is mostly driven by risk tolerance as well as the level of regulation for the specific application. Now, the second thing I wanted to mention was that we've run into an interesting example that speaks to this exact dynamic, where we sold a system to a client with a whole bunch of Class 1 Division 2 certified components, and it was in one of these applications. And what they ended up having to do was field certifications at the system level. So we sold them an assembly with a bunch of certified components. They installed that, and then they brought out a professional engineer onto the site to do what's called a field level certification. So after the PE inspected the actual installed configuration, they were able to certify it at the system level, which was required for that application. Downside is that they had to fly a PE out to every installation to do that field certification, which was very expensive. And so that is an application where that client, for the next round of systems installations, started to think about achieving a system level Class 1 Division 2 certification, because if the entire system and assembly had that certification, you could bypass that field certification and save all the money and expenses of bringing a PE out to a field site. So that's just a very specific example that we've seen where a client has had to shift from C1D2 certified components to a C1D2 certified system, and that was internal cost control on their end, which was really driving that.
All right, very good. Question from Manon. Question is, can you please speak a little bit about PWM versus slow switching charging methods on the controllers, specifically about the interference issues with instrumentation communication protocols such as HART communications, which I believe is highway addressable remote transducer communications. Says, let's see, we have noticed that HART transmitters installed near these solar controllers have problems communicating with PLC over HART. So Brad or Errol, are you able to take that?
I can speak to this because I've addressed this issue over the years. Yeah, there's a few things. Real quick, the frequency that PWM actually works at is 300 hertz. Okay, so it's not all that fast in terms of the pulse charging that is going into the battery. However, the power per pulse and the harmonics that sometimes can be produced that are, multiples of that frequency can and have caused interference. It's not common, but it does occur, mainly because of the power levels with certain types of equipment. That's dramatically reduced over the years as we've gone towards more sophisticated modulation schemes. I'm not specifically familiar with the HART, but there may be a possibility that's more susceptible. In terms of the occurrence, like I said, it's relatively minor. However, there is solutions in both the Sunsaver products and the PPT products, the Sunsaver and ProStar products that allow you to change the 300 hertz to a slow switching mode, which is something that you referred to in your question, either by cutting a jumper or flipping a dip switch. That generally will eliminate it. It charges the battery slightly less well, but it still will eliminate problems in the field very easily with just a simple adjustment. One thing I would comment on is that in PPT, the speeds at which we actually charge and switch the frequency for the charging of the battery is in the kilohertz, the high kilohertz range, in some cases 20 to 40 kilohertz, meaning the power per pulse is dramatically reduced across each pulse, and we've seen it almost completely eliminated, any kind of interference. So bottom line, yeah, it's an occurrence, but it's rare. There's a solution to fix it in the PWM products if needed, and I would highly recommend that you look at PPT as a possible future path, because not only are you going to see the benefits that Errol spoke about in terms of power gains and efficiency and module choice, but you'll probably see those interference issues go away completely.
All right, thanks for that question and answer. A follow-up question here. Let's just make sure we nail this down, because this just came in a couple minutes ago. I know we were addressing this, but this is, again, a kind of a tricky subject. Question here is about the UL logos and ratings again. So the question is, can you clarify regarding UL logo on the SolarTech data sheet, as it means it is UL listed? He says, it seems like it is only ETL listed. So Brad or Errol, if you want to answer that again.
I'll take a first stab at this, and I can send out a chat response as well to the larger group. So my understanding of the question is that this is around the difference between listings and certifications. And Brad sort of alluded to it earlier in the conversation, which is that any of these NRTLs, these NRTLs, nationally recognized testing laboratories, any of them can certify to really most of these standards. So, Intertech can certify a product to a UL standard, or CSA can certify to a UL standard, and vice versa. And so all of these products that we've described are certified to these standards, and we can get the listing numbers for the NRTLs and all that sort of stuff. But UL listed, my understanding, is slightly different, because that basically implies that UL was the certifying body. Has not to do with the standard it was certified to, but the body that did the certifying. And so this UL listing has been this desirable thing for a variety of reasons, but not a lot of people want to work with UL directly as a certifying body because they're expensive and slow compared to the other options. So this is a dynamic that we've discussed a fair amount. And if I'm understanding the question correctly, and my recollection is correct, some of this may be down to this difference of being either UL listed or certified to the UL standard by a different entity.
Okay, I think you nailed it. One last question that I wanted to make sure we covered. This one goes to Brad. Question is, can the EMC1 Ethernet Minibus accessory and the Morningstar's relay driver, can they be used in hazardous locations?
Yes, they can, with an associated listed host product. Okay, so in other words, the accessories that I covered on the slide earlier, you know, the key ones being relay driver, our EMC, several of our little data communications bridges and adapters, they're not listed to be used standalone. It's typically that they would not be used standalone anyway, because they're not really, they don't have a sole purpose themselves. They work with a Morningstar controller to provide an added functionality or data conversion. So an example would be, if you'd like to, you've got an Ethernet installation at a SCADA site. It's quite modern. It's using Ethernet and Modbus over IP, okay, versus the old serial communications protocols. And you want to add an EMC1 to a ProStar MPPT. The ProStar MPPT is listed to be used in a HazLock location, and the EMC1 was incorporated into the testing plan as a compatible accessory to the ProStar MPPT. Therefore, the EMC1 tested in conjunction with the ProStar MPPT's listing process, they can be used together in that zone, and they're fully compatible. Okay, so we wanted to be sure that when we're doing this testing, that we wouldn't inadvertently exclude any of our popular accessories from being used in the products just because they're in that listing. Okay, like I said, the only exception is an accessory can't be used standalone by itself because it's not listed, but there's really not any way in which that would occur anyway, because it doesn't really have a use in that manner. Okay, I hope that makes it clear. And again, feel free to follow up with us for any clarification, because I know this is tricky. A lot of what we do with our in-house specialists for this testing and our close relationship with the labs is listing numbers, clarifications, documentation, support to help, you know, get this done, and be sure that when you are speaking with an inspector, you're fully supported, you know, of course, by SunWise and Morningstar in these applications, so that you have as smooth a process as possible.
All right, thanks, Brad. I think with that, we can go to the thank you slide, the last slide. I believe we've covered all the questions here. If you have anything additional, you can either go to either the websites that you see here, or contact Errol or Brad directly. Other than that, we're going to close things out. Any other last words that you want to say, Brad and Errol, or are we good to go?
Just a thank you.
Yeah, I'd like to say thanks to Errol for participating, because after having been through the formal presentation, I think between the coverage of the new product features and then Errol's, you know, excellent examples of what these new product models and power ranges can do to a system, and thanks for bringing the data to support that. Even the economics, Errol, I think was really informative and really useful. So thanks for putting all that together.
Absolutely, our pleasure.
Terrific. Okay, so I'm going to close things out, and I will extend my thank yous both to Errol, Brad, and everyone in attendance today. We will catch you next time. Thanks so much.